You ever look at some data and just wonder, is that pattern you're seeing a real, legit trend, or is it just a total fluke? Well, let's get right into it, because today we're going to break down the chi-square test into super simple steps so you can figure that out for yourself. So here's what we've got on deck. We'll kick things off with what this test even is, then get into its key ingredients, observed versus expected frequencies. After that, we'll do the actual calculation, talk about something called degrees of freedom, and finally, figure out what our result actually means. All right, first things first, what is this thing really for? Let's get right to the heart of it. I mean, this is the million-dollar question, right? Think about it. Let's say you're polling people on their favorite car color, and suddenly you see way more people picking green than usual. Is that a real trend, a shift in what people want? Or did you just happen to talk to a bunch of people who love green? How can you know for sure? Well, the chi-square test is the tool that gives us a mathematical answer. It puts a number on the difference between what we actually see, our observed data, and what we expected to see. Then, and this is the cool part, the test tells us if that difference is big enough to be statistically significant or if it could have just happened by random chance. So, to really get a handle on the calculation, we first have to get comfortable with its two key ingredients, the observed frequencies and the expected frequencies. It's a pretty simple idea, but it's everything. Observed frequency, we'll just call it O, is what you actually counted. It's the real world. The expected frequency, or E, is what you would have predicted if nothing special was going on. Maybe based on last year's sales or just an assumption that every option is equally popular. The whole test is just about comparing these two numbers. But what if you don't have something like last year's sales to go on? This happens a lot when you're comparing two things in a table, like maybe looking at how different age groups vote. For any single box in that table, you can calculate what you'd expect to see. And the formula is super straightforward. You just multiply that box's row total by its column total and then divide by the grand total of everybody. It's just a clever way to figure out the no pattern baseline. Okay, this is it, the main event. Let's roll up our sleeves and actually walk through the calculation. It might look a little intimidating at first, but I promise it's just a few steps of simple math. And here it is, the famous chi-square formula. Don't let the symbols freak you out. All it's saying is that for each category, you take the observed number, subtract the expected number, square that difference, and then divide the whole thing by the expected number. That big sigma symbol, that's sigma. It just means add it all up. So you do that little calculation for every category, and then you just sum them all together at the end. That's it. See, we can break it down into 4 clean steps. 1, find the difference. 2, square it. 3, divide. And 4, add everything up. Let's build a little table to keep it all nice and organized. Okay, let's use a real example. Imagine a car dealership polls 150 customers on what color they like, just to see if people's tastes are changing. So the first step is to get our 2 columns of data set up, what they actually saw in the poll, the observed, and what they expected based on last year's sales, the expected. And now we do our first bit of math. We just subtract the expected from the observed for each and every color. So for yellow, that's 35 minus 30, which is 5. For white, it's 25 minus 45, which gives us negative 20. We just go all the way down the column like that. Simple. Step 2, we square that difference. Now this is kind of cool because squaring the numbers does 2 things for us. First, it makes any big differences even bigger, and second, it gets rid of any negative signs. So 5 squared is 25, and that negative 20 squared becomes a positive 400. Almost there. For our last column, we take that squared number we just calculated and divide it by the original expected value, E. So for green, we'll take 225 and divide it by its expected value of 15, and that gives us 15. For white, we take 400, divide it by 45, and get 8.89. Once we do that for every single row, we just have one thing left to do. Add up that entire last column. And boom, there it is. The sum of our final column is 26.95. This one number represents the total difference between what we saw and what we expected. So, now what? What does 26.95 actually mean? You see, a chi-square value of 26.95 is pretty meaningless all by itself. To figure out what it's telling us, we need one more piece of the puzzle. We need to talk about degrees of freedom. Exactly. Is 26.95 a huge, significant difference, or is it basically nothing? Well, it depends on how many categories we were looking at in the first place.
A difference of 26.95 spread across just a few categories is a lot different than that same number spread across, say, 30 categories. And that's where degrees of freedom come into play.
Think of degrees of freedom, or DF, as a way to account for the size of your experiment. It gives us the context we need to judge our chi-square value. Once we have our degrees of freedom, we can look up the correct benchmark, what's called a critical value, to compare our number against. And calculating it is usually super easy. For a simple list like our car colors, it's just the number of categories minus 1. We had 5 colors, so our degrees of freedom is 4. Simple as that. If you have a more complex table with rows and columns, there's another formula, but the idea is exactly the same. It just gives our final number some much-needed context. Okay, we have all the pieces. We've got our calculated chi-square value. We've got our degrees of freedom. Now it is time to put it all together and finally make a decision.
And here's the final showdown. On the left, we have our number, 26.95. On the right, we have the critical value. Now we get this number from a standard statistics table. We just look up our degrees of freedom, which was 4, at a standard confidence level, which is usually 0.05, and the table tells us the magic number is 9.49. That's our benchmark.
And the rule could not be simpler. If your number is bigger than the critical value, you get to reject what's called the null hypothesis. The null hypothesis is just the boring, default idea that nothing is going on and your results are just random. Well, our 26.95 is way bigger than 9.49, so we get to reject that boring idea and say, yes, the difference we saw is statistically significant. That shift in car color preference, it's probably real.
And really, that's the whole point, isn't it? It's not about doing math for fun. It's about having a tool that lets you go from, I think I see a pattern, to I have statistical confidence that this pattern is real. So now that you have this in your back pocket, think about all the data you see every day. What interesting patterns might be hiding just below the surface, waiting for a quick test of significance to bring them into the light?